Greetings everyone, I welcome you back to TV Mathshub. In our previous lecture, we explored different probability distributions, focusing mainly on discrete distributions like the binomial, Poisson distributions, and many others. However, today we shall shift our focus to continuous probability distributions where variables can take any value within a given range. We shall cover different concepts, different examples of the continuous probability distributions. So make sure to subscribe, to like and share this video to support the channel and stay updated with more math lessons. So let's get started. Today we shall be talking about the uniform or rectangular distribution as one of the examples of the continuous probability distributions. We shall begin with the definition. Let us begin by looking at the definition for the uniform or rectangular distribution. A continuous random variable x is said to be uniformly distributed if its probability density function is given by f of x, which is equal to 1 upon b minus a, for all the values of x which are in the range of a to b, and 0 otherwise. So in case you pick any value of x which is outside this range here of a to b, then your function will be equal to 0. We shall now derive the PDF of a uniform random variable. So to derive the PDF of a uniform random variable, we shall basically consider a constant function, that is f of x, which is equal to a constant c. Because when you look at by definition, you realize that f of x is equal to 1 upon b minus a, but a and b when substituted will give us a constant value. 1 upon b minus a will be a constant value. So for us to derive a PDF of a uniform random variable, we shall consider a constant value. So that's why we are considering f of x equaling to c. And this is defined for all the values of x, in the range of a less or equal to x less or equal to b. So from our graph here, we can easily come up with the PDF. So let us consider the area that is enclosed under our line or our curve f of x equaling to c. F of x equaling to c is simply a straight line. So from that, we can easily see that the area enclosed by this line here, f of x equaling to c, together with our limits a and b, will be this area here. And by definition of that area, we can say that area is actually same as this length here, then times this one here, that is like height. So the total area under the total area that is enclosed under this line here is actually 1. So 1 is equal to length. Length is from here up to this given point. So the length here, if this is a and this is b, can be defined by b minus a. So we shall have b minus a, then times the height here is actually c. So the height here is c. So you have 1, which is equal to b minus a times c. 1 is the total area under this function. The total area enclosed by that function here, together with a and b, will be equal to 1. So we can easily make c the subject. C will be 1 upon b minus a. But what is c? C is actually f of x. So our f of x will be equal to 1 upon b minus a. So this will be the PDF of a continuous random variable, but which is uniformly distributed. So our f of x will be 1 upon b minus a for a rectangular random variable or a uniform random variable. Let us now look at some few examples. And example number 1 says the number of goals scored during the African Cup of Nations 2013 is uniformly distributed with a probability density function which is given by f of x equaling to 1 upon 6. 1 is less or equal to x, which is less or equal to 7. So otherwise, f of x will not be defined. So they have only defined for us f of x in the range 1 to 7. So otherwise, we shall not have f of x defined. Now, we are given f of x as 1 upon 6, and the range is 1 less or equal to x less or equal to 7. So we need to obtain the probability that the number of goals scored in any game is less than or equal to 3. So we need the probability of x less or equal to 3. So this will be same as taking up all the values from 1 up to 3, because our x is defined from 1 up to 7. But for us, we are interested in x less or equal to 3. So it will be same as integrating from 1, the least or the lower limit, up to 3, f of x, then dx. This will still be same as integrating from 1 to 3. F of x is 1 upon 6, then dx. So we can integrate this. This will give us 1 upon 6 of x, limits from 1 to 3. So substitute your upper limit. It will be 1 upon 6 into the upper limit is 3. Then put the lower limit, which is 1. So this will give us 2 upon 6. So our probability of x less or equal to 3 will be 2 upon 6. Looking at part B says we need to obtain the expected number of goals in any game at the African Cup of Nations 2013. So to obtain that, we shall have to recall that expectation of x is same as integrating from negative infinity to infinity of x, f of x times dx. This is by definition, and for that case we shall have our limit. The limit that is given, remember our f of x is given as 1 upon 6, and we are given that this is defined in the range of 1 is less or equal to x less or equal to 7. So which implies that we shall have our limit from 1 to 7 of x times f of x, which is 1 upon 6, then dx. And this will be same as having 1 upon 6, then we integrate x from 1 to 7, then dx. So looking at that, we shall have this as we integrate this, and this will be same as a half x squared from 1 up to 7. This can be simplified as, so we shall put the upper limit is 7, so 7 squared upon 2 minus the lower limit, so we shall have 1 squared upon 2. So this will give us this will give us 1 upon 6 into 49 upon 2 minus 1 upon 2. So this will be same as 1 over 6 into 49 minus 1, it will be 48. So we shall have 48 divided by 2. And this will be same as 1 upon 6 times 48 divided by 2 is same as 24. So we shall have 1 over 6 times that. And this will give us 4. So it means the expected number of goals will be same as 4. Now, for the case of part C, they are saying the final is a nil-nil at the end of the game. In other words, they are interested in P of x equaling to 0. So, according to the defined PDF, we have f of x as 1 upon 6 and x taking up all the values from 1 up to 7. So we don't have x defined outside this range. So the range is from 1 to 7, meaning below 1 we don't know. Below above 7 we are also not given the nature of this given function. So for the P of x equaling to 0, we shall be saying the probability does not exist since we don't have a distribution below x equaling to 1. So we don't have a distribution below this and we don't have a distribution above this. So you should be in position to try out this exercise, and it says for a uniform distribution, show that the cumulative distribution function is given by f of x, which is 0 if x is less than a, x minus a upon b minus a, for x taking up the values in the range of a less or equal to x less than b, and 1 for all the values of x greater or equal to b. We shall now look at the expectation of a continuous uniform distribution, and we shall be saying that the expectation or mean of a uniform distribution is given by expectation of x equaling to b plus a divided by 2. So we need to prove this, and we shall prove this expression here for expectation using the definition of expectation. So let us look at the proof. We know that by definition of expectation, that expectation of x is same as integral from negative infinity to infinity of x, f of x times dx. And by the definition of our f of x for a continuous uniform distribution is given by 1 upon b minus a. This is the general expression for which you are having a less or equal to x less than b. And for that case, it means our limits will be from a to b of x times f of x 1 upon b minus a, and then dx. This will be same as 1 upon b minus a. This is a constant value. Then integral of a to b x dx. So this will be same as 1 upon b minus a times, integrate this, and it will be able to give us x squared upon 2 from a to b. This can further be simplified. So the 2 is a constant, we can pull it out of this bracket, and we shall have 2 into b minus a, then into x squared which is having limits from a to b. So from here we shall have this as 1 upon 2 into b minus a times, put the upper limit, it becomes b squared, put the lower limit, it becomes a squared. So this will give us 1 upon 2 into b minus a. This is a difference of 2 squares, so we can have it as b minus a into b plus a. So this will give us, this and this are the same, so they will cancel out. We shall remain with b plus a upon 2. So this will be expectation of x. So when you look at, for example, the previous example that we have done, where we were given our f of x as 1 upon 6, and it takes up the range for x as 1 less or equal to x less or equal to 7. So it means this represents your a, this represents your b. So if you are interested in expectation, then you will simply say it is 7 plus 1 divided by 2, which will give us 4. So when you look at what you get here and the answer we obtained in our previous example, you realize they are the same. So let us now look at the variance. So this is expectation. So we have clearly seen our expectation as b plus a upon 2. So we can as well come up with the variance of the continuous uniform distribution. And by definition, the variance of a uniform distribution is given by var of x, which is equal to b minus a squared divided by 12. So we need to come up with this expression here. So let us see how best we can obtain the expression for the variance. We know that variance is defined by variance of x is defined by the expectation of x, which is squared, minus expectation of x, which is also squared. This is by definition of variance. Now we already know expectation of x as b plus a upon 2. So it means we need to find the expectation of x squared. So let us first consider expectation of x squared. So the expectation of x squared by definition is same as integral from negative infinity to infinity of x squared times f of x. We need to recall that f of x is 1 upon b minus a, for which you are taking up the values of x in that range of a to b. So from there, we shall now consider our expectation of x squared as integral, our range is from a to b, of x squared times 1 upon b minus a, then dx. This one is a constant, so we can place it out, b minus a. Then we remain with integral of x squared dx. This will be same as 1 upon b minus a. When we integrate this, we shall get a third x to power 3 from a to b. So from there, we shall have this as 1 upon b minus a. We can pull out the 3, which is a constant here, and we shall remain with x cubed, the limits from a to b. So this is 1 upon 3 into b minus a multiplied by, we shall put our limits. Our limits will give us b cubed minus a cubed. So we need to put the simplified form for this. So we know that this b cubed minus a cubed can be as well written as b minus a into b squared plus ab plus a squared. So this can be written as this in a factorized form. And from this, we can easily see that b minus a will cancel out. So when b minus a cancels out, we shall remain with b squared plus ab plus a squared divided by 3. So we shall have this equaling to b squared plus ab plus a squared divided by 3. This is expectation of x squared. Now, we said that variance, by definition, variance is same as expectation of x squared minus expectation of x, which is squared. We have expectation of x, we have obtained that. So we shall substitute them to get the value for the variance. So variance of x, so we shall be saying from 1, variance of x is same as expectation of x squared, which we have got as b squared plus ab plus a squared. We are dividing this by 3 minus mean. We obtain mean as b plus a divided by 2. This was our expectation, and this is squared. So we shall try to simplify this. We shall have b squared plus ab plus a squared divided by 3 minus, this can be expanded, and this will be b squared plus 2ab plus 2ab plus a squared, the whole of this divided by 4. We can get the LCM here. The LCM will be 12. 12 divided by 3, we shall get a 4. We multiply it there, it will be 4b squared plus 4ab plus 4a squared minus 12 divided by 4 is 3, so we shall multiply it there, minus 3b squared minus 6ab minus 3a squared. That is what we shall get. So let us try to simplify this further. 4b squared minus this will give us b squared. 4ab minus 6ab, we shall get minus 2ab. 4a squared minus 3a squared will give us a squared. The whole of this is divided by 12. So from there, we can have our variance of x as, when we look at this one here can be as well written as b minus a squared. So when you expand this, you get this. So this is an expansion of b minus a squared. So the whole of this is divided by 12. So clearly we can easily get the expression for variance as b minus a squared divided by 12. If they go on and ask for the standard deviation is the square root of variance, and for that case it means standard deviation will be same as taking the square root of b minus a, the whole of this squared, upon 12. So it will be same as having b minus a divided by the square root of 12. So this will be the standard deviation for a continuous uniform random variable x. let us look at one more example. It says a packaging line consistently packages 20.0 kg per hour. After weighing every package, variation in weights ranging from 18.2 kilograms to 20.4 kilograms was formed. 1. They need us to find the mean, standard deviation, and the probability that a package exceeds the customer requirement. So the most important thing here is to identify the range. Then after identifying the range, you will be able to answer all the questions. Now, the range that is given is from 18.2 to 20.4. So, looking at what we discussed earlier, we said that when you have the range, you can come up with the PDF. Because we know the PDF is same as f of x, which is equal to 1 upon b minus a. So let us identify a and b. So the lower limit is the a and the upper limit is the b. So meaning that a is 18.2 and b is 20.4. So having a and b, you can get f of x. So by simply substituting for a and b in this expression. So let us look at the mean. Mean is same as b plus a divided by 2. Or someone can write a plus b divided by 2. So from here, you can obtain your mean by substituting for a and b. We already know our a is this and our b is that. So as we have said, this one here is satisfied by the range a less or equal to x less or equal to b. So your a is 18.2, your b is 20.4. So this will be able to give us the mean, and that will be same as getting 18.2 plus 20.4 divided by 2, which will give us 19.3 kilograms. Standard deviation, we have looked at the expression for standard deviation, where we said standard deviation is simply same as b minus a upon 2. We have already discussed about this. So you have your b, you have your a, so simply substitute. Your b is 20.4, your a is 18.2, and we are dividing by the square root of 12. This is square root of 12. So from there, we get the standard deviation, and that will be 0.635 kilograms. Let us talk about the probability that a package exceeds the customer requirement. We are given that a packaging line consistently packages 20.0 kg. So which means the customer requirement is 20.0 kilograms. So, but there are variations. However, the maximum variation is up to 20.4. So, in other words, if we are interested in probability that x exceeds 20.0, it will be same as integrating from 20 up to the maximum variation, which is 20.4, of f of x dx. What is your f of x? Your f of x is this. F of x is 1 upon b minus a. You already know b, you already know a. So substitute that expression and you'll be able to get 0.1818. So that is for the different questions on different numbers pertaining what we call the uniform distributions. So you will be able to try some few questions here. Should be able to try the exercise 3.27. So you should be able to try this one out. You should as well be in position to try exercise 3.28. And the most important thing when you are trying these numbers here, first identify the range that you are considering. Then after identifying the range that you are considering, you can easily come up with the PDF, and from that, if you identify your range, then you will be able to obtain the mean, to obtain any probability, and to obtain standard deviation and the variance. So use the same methods that we have so far discussed. So that is exercise 3.28, exercise 3.27. You will also look at the exercise 3.29. Try all these numbers out. Exercise 3.30, and lastly exercise 3.31. And that is where we shall be able to stop in our today's lecture, and we shall be able to start from the exponential distribution.